Hello everyone, welcome back to my channel. And we already discussed a 6 vulnerability in the part 1. So here we discuss about the after that all vulnerabilities. So I think you already see the part 1 and we are discussing here the other vulnerabilities. Our next vulnerability is to understand Delegatecall vulnerabilities, which often appears in upgradable smart contracts architect. To understand this problem, we first need to little bit talk about the proxy contracts. One limitation of smart contract is they are not they are immutable, means we cannot change in the contract. Once a contract is deployed, that its code cannot easily be changed, but many modern DeFi protocols still need the ability to upgrade their logic. To solve this problem, developers use something called a proxy architecture. Instead of putting all logic directly in the contract, the system is split into the two contracts. The first contract is a proxy contract, which store the data and the user balances. The second contract is the implementation contract, which contains the actual logic of that contract. When the user interacts with the proxy forward the call to the implementation contract using the Delegatecall of course. So the execution flow look like a user goes to the proxy contracts and proxy contracts go to Delegatecall and Delegatecall to implementation contract. The important detail here is like how Delegatecall behaves. So when Delegatecall is used, code from the implementation contract is executed, but the storage of the proxy contract is used. It means the implementation contract can be modified the proxy storage variables. For example, the proxy might be store a critical variable such as like owner, admin, implementations or balances. If attacker can control which implement contract is used, they could deploy a malicious implementation. They overrides these storage variables. Let's look at a simplified example. Imagine a proxy contract, the forward call like this: address, implementations and public implementation.delegatecall.message.data. This implementation address is not properly restricted. An attacker could provide their own malicious contract. That malicious contract could contain code like this. There is a malicious contract. Functions attack at the public and the owner is equal to message.sender. Since the code runs using the proxy storage, the attacker could override the owner variable and the gain full control over the contract. This is why Delegatecall must be used very carefully. How prevent this vulnerability? Developers follow the several best practices. First, the implementation address must always be strictly controlled. Only authorized administrators should be able to upgrade the implementation contract. Second, the upgrade mechanism should be well audited proxy patterns rather than custom implementations. Many projects use the upgrade frameworks from the Open Zeppelin, which provide the standardized proxy implementations. When a protocol upgrades, its implementation of developer must ensure the new contract preserve the correct storage layout and does not introduce a malicious logic. Because if the malicious implementation is ever deployed, the attack could gain complete over the control. So like restrict implementation upgrade, use standardized proxy framework and verified implementation contract. These three is important. Then the another vulnerability that appears in the upgradeable contracts is unutilized contract storage. To understand this problem, we need to look how constructor work in Solidity. Normally, when the contract is deployed, its constructor functions runs once and initialize important variables such as a contract owner. For example, constructor owner is equal to message.sender, that is work of the constructor. However, the proxy based upgradable contracts cannot use constructor in that usual way. This is because the implementation contract is deployed separately from the proxy contract. Instead of constructor, upgradable contracts use initializer functions. The functions perform the same setup logic that a constructor would normally handle. Example like a function initialize public that honor message dot sender, but that introduce the new risk. If the initializer function is not protected properly, anyone could call it, and if someone else calls the initializer first, they could become the owner of that contract. This is exactly what happened in the one of the most famous smart contract incident, the Parity multisig wallet hack. In 2017, a major vulnerability was discovered in the Parity multisig wallet hack. Parity provides the widely used of multi-signature wallet for the Ethereum users. The wallet systems relied on the shared library contract that contained a common wallet logic. Unfortunately, this library contract had been properly initialized. Because the initialization functions was still accessible, an attacker was able to call it. By calling the initializer, the attacker became the owner of the library contract. So, after gaining ownership, the attacker executes the self-destruct function on the library. This permanently destroys the contract code. Since thousands of wallets depended on that library contract, those wallets stop functioning. As a result, roughly 150 million worth of ETH become permanently frozen. The funds were stolen, but they became completely inaccessible from the any wallet. Like, this incident demonstrated how dangerous uninitialized contract can be. So how preventing initialization's risk. So modern smart contract frameworks include the safeguards to prevent these issues. Upgradeable contracts typically use as initializer modifier that ensures the initialization functions can only run once. So the example is like function initialize public initializer owner and message sender. This initializer modify ensures the function can only run once, preventing re-initialization attack. Developer must also make sure that initializations happen immediately after the deployment before the contract becomes publicly accessible. By carefully managing the initialization of ownership logic, developer can prevent the attack from the taking control of upgradable contracts. This vulnerability show how complex upgradable smart contracts architectures can become, while proxy patterns provides the flexibility and upgradability that also introduce the new security risks that developer must handle carefully. And then also initialize after deployment and use audited upgrade framework with the OpenZeppelin. Then another category of vulnerabilities is that appear in the smart contract is denial of service attack, DOS attack. Unlike many other exploits we discussed earlier, DOS attacks do not always steal funds directly. Instead of they make a part of the protocol unusable or permanently stuck. This can disrupt the system, block withdrawals for freezing important functions. There are the several ways to denial of service attacks can occur in the simple contracts. Guess limits, like guess limit of denial of service. One common pattern appears when the developers write a loops that iterated over the large array. For example, imagine a contract that process all user in a list. At a first glance, function, distributor rewards, and the public. And for uint I is equal to 0 to I less than user.length and I plus plus. Rewards users I is equal to plus is equal to calculate rewards and user I. Imagine if a contract processes all user in a list. Like at a first glance it seems reasonable, all user are in a list, but the problem appears when the number of users become very large. Every iterations of a loop consume gas. If array grows too large, the transaction will exceed the block gas limit. That means the protocols may become permanently stuck. Then is like a forced revert attack. Another type of DOS occurs when the transactions depend on external code might be fail. Like if the receiver is a malicious contract, it could deliberately revert the transactions. That would cause the entire operation to fail. If these calls happen inside the loop of critical function, the attacker could repeatedly block the protocol from executing the operations. Like, what is the typical DOS attack scenarios? Like, attackers interact with the contract repeatedly. Attackers force contract to store large amount of data. Import functions new loops over massive array. Transactions exceed gas limit. Protocol functions become unusable. There is protocol become unusable. This type of attacks they do. Attacks interacts repeatedly, large data, critical functions loops, and transaction exceeds gas limit, and protocol becomes unusable. So mitigation developer prevent DOS attack, DOS vulnerabilities using several strategies like a batching operation. Instead of processing all user in a one transactions, the work is divided into the smaller batches, like process user 0 to 50, process user 51 to 100, and process user 101 to 150, like that way. This ensures each transactions remain within the gas limit. Then the second is like a pool payment method. Instead of pushing the funds user automatically, the contract allows user to withdraw their own funds. Example like function withdrawal reward public, and uint amount is rewards message.sender, and requires amount less than 0, no rewards to withdraw, and rewards message.sender is equal to 0. Clear balance first to prevent reentrancy, then the bool success payment message, and the require success of transactions failed, or like success or failure. This avoids looping through the many users in a single transaction. Denial of service vulnerabilities highlight how gas limits and the contract design can affect the relatability of smart contracts. Then the next vulnerability, we need to understand the timestamp manipulations. In Ethereum and the other blockchain, each block contains a timestamp that represents the block was created. When the block was created. Developers sometimes use this timestamp inside the smart contract logic, such as time-based events or like auctions, lotteries, randomness generations. However, the block timestamp is not perfectly precise. Validators have some flexibility to when setting the timestamp of block. They cannot set completely arbitrary values, but they can adjust the timestamp slightly within the certain range. This means contract that rely heavily on timestamp can be manipulated. Example, vulnerability logic. Like, imagine a contract that tries to generate a randomness like unit random uint block.timestamp multiply by 2. Okay. At a glance, it might look like a random value, but if validator can slightly modify the timestamp, they could influence the result. Example like attack scenario, what would like user submit the transaction first involving the randomness. Validator sees the transactions in the mempool. Validator adjusts the block timestamp slightly, and randomness calculate changes. Validator or attackers benefits. Like validators also as attacker also. This can affect things like a lottery winnings or time sensitive financial decision. So the best mitigation strategies is avoid rely on block timestamp for a randomness for a critical financial logic. Instead, developers should use external randomness sources such as verifiable randomness functions provided by the Oracle networks, like a chain-link VRF, verifiable random functions, Oracle-based randomness services. So weak randomness in smart contract. The randomness is surprisingly difficult to implement securely on blockchain. The reason is that blockchain are deterministic system. Every node is a network must produce exactly the same result when the executing a smart contract. Because of this, generating an unpredictable randomness directly on chain extremely challenging. Many developers attempt to create a randomness using a block data. Common example of include like block.timestamp, block.number, block hash. However, these values are not truly random. they are either predictable or partially controlled by validators. Attackers can sometimes compute outcomes in advance or influence the values used by the contract. Example of weak randomness attack. Like a typical randomness vulnerability might look like this. The contract generates the random number using the block.timestamp, and the attacker observe that pending transactions. Attacker predict the possible outcomes. Attacker only execute transactions when outcome is favorable. This allows to gain unfair advantages in games, lotteries, and NFT minting systems. So that is a vulnerability logic. Uint random is equal to uint block.timestamp, because the randomness choose by the block.timestamp. So the attack scenario is like a attack where they attack like blockchain games, NFT minting, lotteries, reward distributions. So what is the to solve this problem? Many protocols use verifiable randomness functions, is a VRF. One of the most widely used solution is provided by Chainlink. Chainlink VRF generates randomness in the way that cryptographically secure, like immune to prediction of manipulations, unpredictable. Means like no actor can forces to outcome before it's generated. Verifiable on chain. Anyone can confirm the randomness was generated correctly, that wasn't tampered with. This allows smart contract to use random numbers without relying on the manipulating block data. Weak randomness vulnerabilities may seem harmless, but they can completely break the fairness of the decentralized application. That is the why modern protocols rely on a cryptographically secure randomness providers rather than the simple block variables. So they are using this secure way for the blockchain games, like they have card draws, loot box outcomes, or like NFT minting, rare trade restrictions, distributions, surprise reveals, and lotteries and prize draws, fair winner selections for that, and reward and distributions, economic incentives. Up to the point, many of the vulnerabilities we discussed were the coding mistakes. For the example, incorrect access control, unsafe external calls, arithmetic bugs. However, some of the most dangerous DeFi exploits happen when the smart contract code itself technically correct. So how that happen? This vulnerability comes from logic errors in the protocol design. In other words, the contract executes exactly as written, but the economic model behind the protocol has weakness that attackers can exploit. So this is especially common in the complex DeFi systems such as lending protocols, derivative platforms, and automated markets. A well-known example of this type of exploit is Euler finance hack in 2023. Euler lending protocol suffered an attack that resulted approximately 197 millions of dollar in losses. Interestingly, the exploit was not caused by the simple coding bug. Instead of the attacker found a way to manipulate the protocol liquidation logic and internal accounting system. The attacker combined the several techniques together, including a flash loan and liquidation manipulation, and they applied like simple attack flow. Attacker takes the large flash loan first. Attacker deposits assets into the protocol. Attacker manipulates the internal debt positions, and liquidation mechanism became the exploitable. Attacker triggers the liquidation rewards repeatedly. Attackers then after attacker extract the large amount from the fund, flash loan is repaid and attacker keeps the profit. Because of this exploit relied on the economic behavior rather than the simple bug, detecting it's extremely difficult. So the traditional security tools such as a static analyzer or a linters cannot easily detect these kinds of vulnerabilities. So why economic design matters? If DeFi smart contracts behave like automated financial system, every function interacts with the incentives, liquidity pools, collateral rules, and the token economics. If the incentives are poorly designed, attackers can exploit them even if the code itself is correct. That is why the modern protocol development requires economic modeling and the adversarial simulations. Developer must think about the question like, what happens if someone controls large amount of capital? What happens if the price suddenly move dramatically? Can attackers manipulate the system's internal accounting? Many modern security audits includes economic stress testing to detect these vulnerabilities, because when DeFi protocol manage hundreds of billions or millions of dollars, even small logical weakness can lead to be like too much very big loss. The next category of vulnerabilities involves cross-chain breaches. Breach allows to asset move between the different blockchains. For example, user might want to move tokens from the Ethereum to another network such as Solana or BNB chain or Polygon. Since the blockchain cannot directly communicate with each other, bridges act as intermediators. How bridges work? Typical bridge follow a two-step mechanism. First, the asset is locked on the source chain, and the second, a wrapped version of a token is minted on the destination chain. The chain look like this, like user send a token to the bridge on a chain A. Bridge locks token in a smart contract. Bridge verify the deposit, and bridge mints wrap token on the chain B. When the user want to return the asset, the process happens the reverse. Wrap tokens are burnt on chain B, and bridge verifies the burn event, and original tokens are unlocked on the chain A. This mechanism allows to asset move between the blockchain. However, the bridges also introduce the very large security risk, because the bridge contract typically holds a huge amount of locked assets. If the bridge is compromised, attackers can mint tokens without locking any real assets. Why bridge as major target? Because cross-chain bridges have become one of the largest attack surface in the crypto. In fact, several of the biggest crypto hacks in the history involve the bridges. Let's look like few examples here. Ronin bridge hack in 2022. One of the largest crypto hacks ever was Ronin network hack. The Ronin bridge was used the popular blockchain game Exile Infinity. Attackers managed to compromise several validator key responsible for the verifying bridge transaction. Because the bridge required only a limited number of signatures to approve withdrawals, the attacker were able to forge a withdrawal transactions. As a result, they drained approximately $625 million worth of assets from the breach. The second was another incident was Wormhole bridge hack. In this hack, the vulnerability exists in the bridge signature verification logic. The attacker managed to bypass the verification process, mint wraps tokens without providing the required collateral. This allowed them to mint approximately $320 million worth of ETH on the Solana network. Then another notable case was like a Nomad breach hack. The vulnerability occurred due to the incorrect contract update that accidentally allowed any transaction to be considered valid. Once the bug was discovered, many users began copy and exploit transactions. This created chaotic situations where hundreds of addresses drained funds from the breach. The total losses were approximately $190 million stolen. So the common breach vulnerabilities, most breach exploits fall into the few common categories. Validator key compromise. Many breaches are rely on the small set of validator to approve cross-chain messages. If attackers gain the access to the enough validators, they can forge withdrawal transactions. Then the signature verification flows. Some bridges rely on the cryptographic signatures verify cross-chain messages. If the verification logic is incorrect, attacker may be able to bypass the validation process. Message replay attacks or like logic errors. Some designs attackers can reuse old messages from the one chain and replay them on the other chain. If the system does not properly track messages status, fund can be withdrawn multiple times. So the cross-chain bridges are extremely powerful infrastructures for the blockchain ecosystem, but they are also represent one of the most complex and risky components in the Web3 architecture. Because they are connect multiple blockchain together, a vulnerability in a breach can affect assets across several network at once. This is why the breach security has become one of the most important areas of research in the modern blockchain development. Then another important vulnerabilities that appears upgradable smart contract system is a storage collision. To understand this problem, we need to briefly revisit how upgradable proxy contract works. In proxy architectures, the proxy contract stores all the data, and while the implementation contracts contain the logic. When the function is called, the proxy forwards a call to the implementation contract using the Delegatecall. Because of how Delegatecall works, implementation contract reads and writes directly to the proxy contract. This means the storage layout must remain exactly consistent across upgradable. If the layout changes incorrectly, the contract may start reading or writing data in the wrong storage slots. Like example, like imagine the proxy contract has a following storage layout. So slot 0 is the owner and slot 1 is the balance. Okay, now imagine the new implementation contract introduce the different variable orders, like slot 0 as a balance and slot 1 as a owner. Now the contract interacting the same storage slot differently. This causes storage collision. Like for example, what used to be the owner verifiable might now interpreted as a balance. Balance might override the ownership data. Administrative privileges could be corrupted. This type of error break the protocol completely. In some cases, it may allow the attackers to gain control over the contract also. Like protocol deploys the proxy contract. Proxy storage critical variables. Proxy stores the critical variable. Protocol upgrades the implementations. New implementation changes the storage layout, and contract reads the wrong storage slot. Protocol state becomes corrupted. So how the developer can developer prevent these collisions by the following, by the strict upgrade patterns. One of the common techniques is the preserving storage space using storage gaps. If u in 256 array 50 in bracket 50 private dash gap, this reserve the extra slots of the future upgrade can add verifiable safety. Most production protocols rely on upgradable frameworks from the OpenZeppelin, which enforce the safe storage layouts. Another important vulnerabilities, there is a signature replay attacks. Many modern protocols allows user to sign message off chain instead of the sending on chain transaction directly. This commonly used for guestless transactions, token approvals, permit based transfer, meta transactions. The idea is simple. The user signs a message with the private key. Then someone submits the signed message to the smart contract, which verifies the signature and execute the request actions. However, if the contract does not properly track whether the signature has already been used and attacker can reuse it, this called the replay attacks. What is the scenario of this? Like user signs the withdrawal message and in the off chain, attacker obtains the signed message and attacker submits the signature to the contract, and withdrawal executes, and the attacker submits the same signatures again, and contract processes withdrawal again. Like a two type of the contract does not track the signature usage. Why this happened? Because the contract does not track the signature of usage. The attacker can repeat the transactions multiple times. This could allow the multiple withdrawals from the single signed message. So there is a how verification code that happened. That a function withdraw address user u in 256 amount bytes memory signature and requires a verify signature user amount signature. Then balances of user that minus from the amount. Payable user dot transfer amount. Okay, if the contract does not whether the signature has already been used, it become vulnerable to replay attacks. So how like we can do the mitigation technique for that one? Developers prevent replay attacks by including the unique identifier signed messages, like common like a nonce, chain ID, deadline. Nonce means like a each user actions includes the unique number of increments after use. Like a unique nonce is a unique sequentially increasing number tied to the user account, ensuring each transaction have a distinct identifier, the one number on the one nonce for the one transactions. Chain ID ensures the signature cannot be reused the different blockchain. Like a specific identifier for the blockchain network is preventing signature from the being replayed from the other chain is the chain ID, because the different chain ID have a different chain ID. Deadline ensures the signature expired after a certain time, a timestamp after which the signed message become invalid, limiting its window of usability. So the many protocols implement these protections using EIP 712 type signature, which provides a standardized and the secure way to structure and signed message off chain. The next is the self-destruct opcodes. Self-destruct vulnerability. The Ethereum virtual machine include the powerful instructions called self-destruct. This opcodes allows the contract to permanently remove itself from the blockchain. So when the contract self-destruct, two things happen. First is the contract code is removed, and any remaining ETH in the contract sent is the specified addresses. So self-destruct is like a payable honor. While this features was originally designed for the cleanup and the contract upgrades, it introduced several risks. Some protocols relied on the external contracts for the implementation logic. If one of those contract self-destruct, dependent system could break. For example, like a contract might call addresses where code no longer exists. Critical logic could disappear. Funds might become inaccessible. Like example of a risk scenario that happen like that way. Protocol depends on external contract. That external contract includes the self-destruct functions. Attacker gains the control of the contract and attacker executes this self-destruct, and dependent protocol loses critical functionality. So the older DeFi system sometimes relied heavily on the shared library contract, which made the risk more severe. Here is the self-destruct scenario. Protocol depends and like external destructs happen, attackers gains, and here is the update of Ethereum protocol update. To reduce this risk, Ethereum introduced improvement to the behavior of self-destruct. One of the important change came through EIP 6780. This update modified how self-destruct works and limited its effects on existing contracts. However, the legacy smart contracts deployed before this updates may still contain the vulnerabilities related to the contract destructions. These final vulnerabilities demonstrate the smart contract security is not just about the correct logic. Developer must also consider how contract interact with the storage layout, external signatures, and understanding this risk is essential for the building secure decentralized system. The next is another type of vulnerability is gas griefing. Gas griefing attacks occur when an attacker deliberately causes a transaction to consume excessive gas so that the transaction fails to become too expensive or to execute. To understand this, remember that every operation in the Ethereum virtual machine consumes gas. If the transaction exceeds the gas limit, it will fail. Attackers can take advantages of that by triggering contract logic and becomes extremely expensive to execute. Like example one of that, expensive loop. Consider the function that loops through the large array. That function iterates through the user control array. In attacker significantly increase the array size and loop gas cost might exceed the block limit. Function process user and public. For u int I is equal to and user length is process users I. The simple functions is look like a simple function. If an attacker manages to increase the size of the user array significantly, the loop could consume the more amount of gas. Eventually, the function may exceed the block gas limit and become impossible to execute. Then the large return values. Another from the gas griefing involves returning large amount of data. That function get all users, public view returns address, memory, and return user. If the user's array become extremely large, returning the data could consume excessive gas and cause the transactions of fail. So here's the gas griefing attack flow. Attackers interact with the contract repeatedly. Attackers inflected data structures like array or mapping, and victim calls expensive functions. And gas cost becomes extremely high, and transactions fails become unusable. So how we can prevent this? To prevent the gas griefing attacks, developer must ensure the operations remain bounded. This means the function should avoid logic that scales with the user control data size. Instead of the processing large array in a one transaction, developer can process data in the smaller batches, like limit the size loop, avoid returning the large data structures, designing the contract with a predictable gas usage in the essential for the maintaining reliable protocol operations. Then the next and last is the final vulnerability we discuss is upgradability risk. Many modern DeFi protocol use upgradable smart contracts so the developer can fix bugs and add new feature without redeploying the entire system. This system typically rely on proxy architecture where the logic contract can be replaced with the new implementation. While this provides flexibility, but it also introduces a major security concern. The entity that controls the upgrade mechanism effectively controls the entire protocol. How that look like upgrade scenario? If an attacker gains to the admin privilege controlling upgrades, they can replace the implementation contract with the malicious one. Like protocol uses the upgradable proxy. Attackers gains the access to admin key, and attacker deploys the malicious implementations in the contract. Proxy is upgrade to malicious logic, and malicious contract transfer protocol funds. Attacker drains the assets. Because the upgradable contracts often control the large amount of assets, compromising the upgradable authority can be lead the big loss. How securing the upgradable smart contract? Multi-signature governance, like multi-signature control. Instead of one private key controlling upgrades, many protocols use multi-signature wallet. This means multiple approvals are requiring before the upgrade can be executed. A widely used multi-sig solution is safe wallet, like is safe. So time lock upgrades. Another protections mechanism is time lock upgrades. Upgrades are scheduled and execute after a delay. For example, like upgrade proposed and 48-hour waiting period and upgrade execute. This delay allows the community to review the proposed changes and react if someone suspicious appears. Decentralized governance. Some protocols go even further by transferring upgrade control to decentralized governance system. Token holders can vote on the protocol changes. This reduce the reliance on centralized administrator and improve transparency. Upgradable contracts provides powerful flexibility, but they must be designed carefully, because if upgradable authority is compromised, attackers can bypass all other security mechanisms and take control the entire protocol. We have now explored the key lesson from the DeFi security is like over the year many vulnerabilities have saved the security landscape decentralized. We have now explored the wide range of vulnerabilities that have shaped the security landscape of decentralized finance, from the classic issue to like reentrancy, arithmetic blocks, but more complex such as oracle manipulations, flash loan attacks, breach exploit, governance risk. And if there is a one important lesson that emerged from all these incidents, it's this: like smart contract security is not just writing contract solidity code. Many of the largest DeFi exploits did not come from the simple programming mistake. Instead of they came from the deeper issue such as fluid economic assumptions, weak oracle systems, poor upgrade governance, unexpected interactions between the multiple protocols. Modern attackers are highly sophisticated. They often combine multiple techniques in a single exploit. For example, an attacker might take a flash loan, manipulate price oracles, trigger a liquidation mechanism, and extract the profit all within a single transactions. This means a developer building a Web3 infrastructure must assume that their system will operate in a fully advisable environment. Every function should be written with the assumption that someone will try to break it. Every dependency should be analyzed carefully. And every external interactions must be treated as a potential attack surface. This is the why smart contract security today requires the much more than the just good coding practices. It requires the rigorous testing, comprehensive audits, continuous monitoring. Protocol often rely on multiple layers or defense, including like a formal verification, automatic testing frameworks, independent security audits, bug bounty programs, and real-time monitoring system. Even the security never completely finished as the DeFi ecosystem continues to grow. New financial primitives are introduced. New attack vectors will continue to emerge. For the developers, it means security must be treated as a core part of development cycle, not something that is added later. Because a decentralized system, the code itself become the financial infrastructure. And when billions dollars are controlled by the smart contracts, even a small vulnerabilities can lead to a massive concurrence. So here the secure smart contract practices also there. So now our topic, and we define all the 18 vulnerabilities, how that exploits happen, how the prevent we can do, all are complete. I think all you are understand how DeFi exploit is so much big and how we can prevent that. So bye bye everyone.